Good evening, Akhleshwar.
Good evening, sir. How are you?
Good. Looks like people have exams.
Yes, sir. This Sunday we are having the exam. Coming
Yeah.
Sunday.
So maybe people are preparing and they did not join.
Yeah, maybe.
Yeah. But still, we'll discuss if you stayed, at least the assignment.
Yes, sure, sir.
Om is also here. He is, yeah, he's connected now. I think we can start now. We won't wait much and we'll finish it as soon as possible. All right. So,
Sure, sir.
yeah. So the first question is when the center of gravity of
So the
aircraft
screen is not visible.
screen is not visible. Oh, sorry. I did not share. I did not share the screen. So let me share the screen. Yeah. Tell me when it is visible.
Yes, sir. Now it is.
All right. So when the center of gravity of the aircraft move rearward, then the effect on long period mode will be. So are you aware of what are long period mode and short period mode?
No, sir.
No.
These terms I'm not familiar with.
So why did they ask questions like this in the assignment? I mean, I'm not sure if they even teach it in this course. Have you gone through
Uh,
the lectures?
Not all the lectures I've been able to go through
Uh,
since I was also occupied with my college academics. So
yeah, yeah, right. Did you go through the lectures and did you see they even discuss long period and short period modes?
no, sir. I've seen all lectures, but not anything like that.
Yeah, yeah, I'm sure they haven't discussed because this is something flight dynamic stuff. And since the question has come, so we'll look at these things briefly. Uh, yeah.
So in the Sunday exam, will it be a simple one, or will it they will make it complicated like this?
I think they will take simple exam. Every year they take simple exam.
Yeah, the previous semester experience was easy, but this I don't know what they are going to do.
It'll be easy actually. They want to keep it simple for everybody. People from different backgrounds take these courses online,
Mm-hmm.
so they can't make it difficult.
And will the paper be more focused on numericals or theory part?
Numericals, I believe, mostly numericals. So
Mostly
yeah,
numericals. Okay.
what is happening is I'm recording this video on my computer also, so it is making my computer lag. Why I'm recording this? Because they send me these video links quite late, but I also need a certificate for teaching. 29 is my deadline, so I have to upload this video right after I finish this session. So for that reason I'm recording it myself, uh, because the link is given to me from IIT Kanpur, and they send these links late, quite late actually. So my computer is not cooperating, but still I just want empty space. Now we've gone through quite a lot of stuff. All right, so uh, you guys know Newton's laws, right?
Yes, sir.
So you're aware that if you have a rigid body, for example, this is a rigid body, if there is an external force being applied on it, then let's say it has only one dimension, it can only move in x direction. So you can write that this is equal to the F external, right? That's how you write, right? Or in other words, x double dot is equal to Fx. Something is missing? Yeah, mass of the object. So that's how you write Newton's second law for a rigid body in one dimension, and when it is not rotating. But the thing is, the aircraft is a rigid body. Uh, it translates as well as it rotates. So because of the rotations, it also experience basically a change in its orientation, right? So when we fly aircraft, we want to uh, keep control on the attitude as well as its location where it's moving. So what happens is, for an aircraft, these equation this pretty simple equation will be it'll become a little difficult. I'll show you how you derive that. So what will happen is, you have an aircraft or maybe any rigid body. You attach a frame on it, and I call it body frame. Okay, you guys are aware of reference frames, right?
Yes, sir. Yes.
Yeah, so it won't be something new for you,
Yes.
yeah, you're aware of it. So I'm calling it body fixed frames, which means if the body rotates, this frame also rotates. Okay, so if body goes in some other orientation, for example like this, so the frame will rotate with the body. Now this whole thing we are trying to capture with respect to some inertial frame, and for all practical purposes, an inertial frame is sitting on earth somewhere, and your plane is flying or any rigid body is moving through space. Now because we move in three-dimensional space, so we have three directions: x, y, and z, right? And we have sensors uh, on board the aircraft that measure acceleration and angular rates. So what we measure is, we measure acceleration in x direction, acceleration in y direction, in z direction. Similarly, we measure angular rates in x direction, y direction, and z direction. So these sensors are placed on board. All measurements are being taken in the body frame. All right, and we are observing the motion in a inertial frame. So there are two frames. Okay, so what I'm saying is, let's write the angular momentum, not the angular momentum, the linear momentum for translation of this aircraft as mv. Okay, now what is v? V has three components: u I cap, either it's bold or it's capital; v j cap, which is small; w k cap. So you have a velocity vector, and that is written in the body frame. So these components of u v w are resolved in the body frame. So p is the linear momentum in the body frame. Now, if I differentiate this linear momentum with respect to time and with respect to inertial frame, whenever you differentiate a vector, you have to specify the frame of reference in which you are differentiating it. Okay, so I'm writing n to note that we are differentiating everything with respect to inertial frame, and that is what the Newton's law is, right? Differentiation of uh, linear momentum
Momentum. Rate
in
of change of momentum.
inertial frame, right? So
Yes.
yeah, but the thing is, this mv is in the body frame. So how we bring it in the inertial frame? This f external is now in the body frame. Okay, so what we do is we call there is something called transport theorem. So let's say you have a vector a, you differentiate this vector with respect to inertial frame, but you know its components in the body frame. So what you do, you first differentiate in the body frame, and then what is the angular velocity of body frame with respect to inertial frame, you take a cross product with that. Okay, omega cross a. So this little relationship is called transport theorem. You can derive it, it's pretty straightforward, but I won't cover it because it is usually taught to you in dynamics course. So this is something called transport theorem. You can remember the result. The idea is, if you know a vector in a particular frame, let's say body frame, and you want its differentiation in some other frame. Okay, for us it's inertial frame. Then you have to uh, add a cross product of this vector a with respect to uh, angular velocity of the body frame with respect to inertial frame. So it's a little complicated, but I hope you get the idea. So what happens here is, we will simply differentiate mv dot plus omega cross mv. Okay, so that becomes the relationship for us of the dynamics of an aircraft, translation dynamics of an aircraft when it's moving. Okay, so f external, all external forces, m v dot, which means there are three components in it: u v w, and this is omega cross. Then you can simply keep m outside, omega cross v, or rather you can divide by mass. You have v dot plus omega cross v. Now, how many equations we have in this one equation? How many algebraic equations we have, guys? See, I see one vector equation. It's a vector equation, but how many algebraic equations we have within this one equation? There are three. Can you tell me how? Okay, so I'll explain. You have x component of the force, you have y component of the force, and similarly you have z component of the force. Similarly, you have u dot, v dot, and w dot, three components of the velocity differentiation, and similarly a omega cross v. So there will be some terms. Let's execute what's there. This is ijk, omega is simply pqr, v is simply u v w. So what is the answer? Just tell me, what is the answer for I cap? Am I audible?
Sir, audible.
Yeah. So,
Uh,
what will be the answer for ICAP?
it will be Q into W minus V into R. Q
V2R.
W V R.
And for JK?
P W minus U R.
Yeah, but minus of that.
Yeah, it will be negative.
So PW minus UR, which means UR minus
U R.
PW.
Yeah,
And for the last
negative.
one,
P V minus U Q.
yeah. So now you have three equations. Look at them again. Fx is equal to U dot plus some QW minus VR. Fy is equal to V dot plus UR minus PW. Let's call them accelerations instead of forces. AX, AY, and AZ. And that will be W dot plus PV minus QU. So now what happens is these things are actually from the dynamics. Okay, they come because of the Newton's law. But what is the source of these accelerations or the forces? Okay, what is the source of these forces or accelerations? Any suggestions? What is the source of external force on the aircraft? This is the question.
Sir, the free stream air that is coming, external force.
So combined, they are aerodynamic forces, propulsive forces, force of gravity, right? Is it?
Yes.
Yeah. So these are the forces. What happens is you resolve all these forces in three directions. So you will find out Fx of aero, F propulsion in x direction, force of gravity in x direction, right? Similarly, you will do this for y axis and z axis, and you'll substitute everything right here in the on the left side here, and then you have complete the translation dynamics of the aircraft and the forces it is experiencing because of propulsion, gravity, and aerodynamics, though they are external forces, and these are your derivatives. So ultimately what we have is derivatives of velocity, okay, in terms of forces. That's what we wanted. So we have translation dynamics. I'll show you from some pages of the book just to give you an idea what we were doing. Okay, so I go to the dynamics chapter. By the way, this is Nelson. So what we have just did is we've derived these equations here. Uh, you see, u dot plus certain terms of QWRV, V dot plus something. If you divide by M, then everything is similar what we've just derived. Okay, these are force equations. And here, this is the components of gravity in all three axes. Theta and phi are some angles. They are orientation angles. They are used to resolve the force of gravity in the body frame. And XYZ are basically propulsion and aerodynamic forces. So they might have specified somewhere what are X and X, Y, and Z. Let's see. Yeah, propulsive, and these are the propulsive forces, and somewhere aerodynamic forces. So ultimately, the idea is 3.38 is that equation, and you have to find out a way to compute the force of aerodynamics, which are basically lift and drag components on all three aircraft body axes. Then you have all three equations. Similarly, you derive moment equations. I'll give you a brief idea how moment equations are derived. So we'll proceed as earlier. We'll say we have angular momentum in the body frame, which is j omega. J is the inertia matrix of the aircraft, and omega is basically PQR. So J is nothing but IXX, IYY, IZZ. You guys know what inertia matrix is, right? I expect you to know that.
Rough idea.
Yeah, rough idea. Huh? It's inertia, moment of inertia, nothing more than that. So this omega is in the body frame, and omega b is nothing but PQR. We have used these quantities in the previous equations. We apply Newton's law. We say we describe HB in the body frame, but we want its differentiation in the inertial frame, right? So that will be your M external, the external moments. If you do that, what will you end up with? You will end up with something like this: J omega B differentiated. J is constant. Then your omega cross omega B cross J omega B, right? J omega B was the H, and here it will be L external. Also, notice there are three equations here. Uh, M external contains three moments: moment about x axis, y axis, and z axis element. Similarly, you will when you multiply this inertia matrix with the PQR, so there will be terms IXX, IXY, IXZ. So there will be three terms: IXXP, IXYQ, something like that. And all of those terms will sit here, right, in the first equation. Similarly, second equation and third equation. There will be some terms from here also, the cross product terms. Okay. So it will constitute finally these equations, the moment equations you see here, right? IX, they've written it IX. Okay. So IXP dot and so on, these equations. So these are moment equations. Now, there should be a way to represent the attitude of the aircraft, and we are representing that attitude with Euler angles. I'll just give you a brief idea what Euler angles are, and why I'm giving you this brief idea is to answer the first question. I mean, because it uses certain terms that you're not familiar with, so I want to go to those terms, because I just want to give you some idea that okay, this is how dynamics is written and what happens after that. So we want to now understand what Euler angles are. So Euler angles are nothing. Imagine there is an inertial frame. Okay, you have three axes x, y, and z. Now a rigid body, for example, an aircraft, is oriented in some fashion. Let's say like this. My drawings are bad, very bad. Okay, so this is let's say your aircraft. Okay, and you have tail, you have some sort of wing. Okay, this is your aircraft. This is your body x-axis, and maybe this side is your not this side, this side. This is your body y-axis, and with respect to inertial frame, there is some angle with horizontal plane. Let's say this is some theta. Okay, your airplane might be having some phi angle also, some roll angle also, right? Phi, theta, and psi. So the point is, how do you describe this orientation? Like which way the body frame is oriented with respect to the inertial frame here. I mean, how do I move a vector that it aligns with xb, or how do I move a frame that initially coincides with xyz of the inertial frame, and when I rotate it, it aligns with the xyz of the aircraft. So what are those angles? We define them as Euler angles. All right. So the idea is, the first rotation that you take is with respect to z axis of the inertial frame, and then first rotation you call it heading psi angle. So what happens is x axis changes to x dash axis, and y axis changes to y dash axis. Okay, by a rotation of psi. So the first rotation is psi about z axis of the inertial frame. First rotation. Second rotation is with respect to y axis, the newly formed y axis. You take a rotation. So what will happen is, you're taking the rotation with respect to y, which means x and z will change. So your z, let's say, go there, and your x go there. You have some theta. Second angle is theta. You call it the pitch angle. Okay, and this is about y dash axis. Okay, now your z axis is here, your x axis is here, and your y dash is already there. Now you take a third rotation about the x axis, which is phi roll angle. So now your x dash will remain here, and what will happen is x double dash, actually x double dash will remain here, and then y and z will move. So if you have a roll, your y will go there with a certain phi. Similarly, your z will go with a certain phi. So this is the way you define rotations. Three angles that you have defined, they they will align your your frame with your inertial frame with the body frame of the aircraft. So you basically know which way the aircraft is oriented. It might seem little complicated at the moment, but just bear with me. I'm just giving you some conceptual idea what these things are. All right. And now you also want to understand what is the relationship between the derivatives of phi dot, theta dot, and psi dot with respect to the angular rates that you are measuring in the body frame. So they are connected with certain function, and I'll show you those relationships here. Now, body angular velocity is in terms of Euler angles and Euler rates. So this is how they are connected. These are rates. There are proper derivations for this. So I'll skip those parts. Okay. And the last thing we need to discuss is what else we have. We've discussed kinematics. We have discussed yeah. This is the last thing that we need to discuss. So now we want to describe the aircraft position x, y, z, and its derivative basically. So basically x dot, y dot, and z dot. So there is a rotation matrix that transforms body frame to inertial frame, and you have u, v, w of the body frame. So these are the velocity you are measuring on board, and through a rotation matrix, you find out the derivatives. So you can integrate and find out the position of the current position of the aircraft. So let me give you some sense what we've done so far. We have understood that external forces will somehow generate the derivatives of velocity. Okay, that is the thing we have understood. Now you can integrate this equation, and what will the result of this? You will have velocity. Now this velocity will drive the derivatives of position xyz, and by integrating this equation you can find out what is the position. So you know the forces, you know the velocity, you know the position of the aircraft, how it's moving in space. Okay, similarly you have external moments. Those external moments generate the derivatives of omega, angular rates. You integrate these omega derivatives, you find out what are your angular rates. Okay, once you have those angular rates are connected with they're driving, omega is driving the derivatives of Euler angles, phi, theta, psi, right? When you integrate the second equation, you have phi, theta, psi, the Euler angles. So you can call it angular position, angular velocity, translational position, translational velocity. Everything you have now for the aircraft. Okay. So these 12 set of equations, 3, 3, 3, 3. So total 12 equations you have to integrate to find out what the aircraft is trying to do. And all those 12 equations are listed here. So these are the velocity equations, and this is the rotation matrix that I was talking about. It is written in terms of Euler angles. Okay. So this is summary of kinematics and dynamics equations. Now, what happens is these equations are fully nonlinear. I mean, Q is being multiplied with W, so fully nonlinear in a sense. Okay, so these fully nonlinear equations, see here, Q is multiplied with R. So these fully nonlinear equations need decoupling or linearization basically. So in this book, they call it small disturbance theory. In general, what they are doing is they are doing Taylor series expansion about an operating point. So whenever aircraft is operating in cruise, you don't need these complicated equations for that analysis. You need approximate version of these equations, and that's what they are trying to do through small disturbance theory. And what will happen ultimately is, instead of computing the net x that is operating on the aircraft, we will require what is the change of x on the aircraft. So we estimate that x as delta x, okay, the force, change of force in x direction basically. So, and it is connected with change of velocity in x direction, y direction, elevator angle, throttle of the aircraft. So that way we call it small disturbance theory, है ना? And then we derive the linearized version of these equations. Okay, so we have a linearized version here. These are called longitudinal equations. These are called lateral equations. Longitudinal equations involve motion in x-axis, z-axis, and rotation about y-axis. So basically pitch motion. So this is pitching moment. You have change in basically z direction and changes in x direction. So two translation and one moment equation. They are called longitudinal equations. And lateral equations are translation equation in y-axis and these rotational dynamics in uh, x, and this is in x-axis and this is in z-axis. Okay, so these are lateral equations. So finally what happens is, you see a lot of parameters in these equations, these derivatives. If you see them right here, they are np, yp, yv, mw dot, mu, zu. These are called stability derivatives, which means zu means differentiation of force in z direction with respect to velocity in x direction. So how does force on z direction changes when velocity in x direction changes? So these parameters are estimated. They are aerodynamic parameters. They are called stability derivatives. So for a given aircraft, you know the methods to compute them somehow from testing in wind tunnel and other methods. Okay. So these equations, these numbers will be given to you. Then further, we go to the next chapter. Okay, we'll skip this part how they are computed. We directly go to the next chapter to explain you what really how those parameters are actually used. So now look here. We are looking at a different form of those equations. We had acceleration in x direction u. So for u we have delta u dot z direction. Then we have this is pitch rate, basically rotation about y-axis, and then the pitch angle. Okay, and these four are connected for they are called basically longitudinal motion of the aircraft. And how do you affect the longitudinal motion? Through elevator and through this throttle. So throttle will basically change the force in x direction and z direction, and this elevator will control the rotation about y-axis, the pitch control. Okay, so this is the dynamics in they call it state space form, but you just understand this is simply rewritten version of those equations that we were looking in the last chapter. Okay, so ultimately, someone will give us these numbers for an aircraft, and by looking at this matrix, this 4x4 matrix, this matrix will exhibit certain behaviors. I'll tell you. So what happens is, when you take eigenvalues of this matrix, this particular matrix, okay, not this. This is control matrix, and this is called system matrix. So if you do not apply any controls, so this input, this will go to zero. Everything goes to zero when there are no inputs. Right now, you have only this natural dynamics of the aircraft. You call it longitudinal dynamics. Now your job is to understand, if you perturb the aircraft from whatever it is doing in a cruise, so how it will behave afterward. So there are different modes that the aircraft can behave based on where the eigenvalues of this matrix are. So the idea is, there are two kinds of motion, longitudinal approximation. One of them is basically phugoid mode, long period, and the other is short period. So in phugoid mode, what happens is instead of four variables, we only look at two variables, u and theta, and other two variables are zero. The changes in those variables are zero. So you have basically phugoid mode. Okay, so this is 2 cross 2 matrix. So what we did, we simply said change in w and change in q dot are zero. So we are left with only phugoid mode. So we can excite phugoid mode basically by these assumptions. Okay, so when we this 2 cross 2 matrix, we can basically find out the eigenvalues of this matrix, and that is exactly what we are doing here. We are finding out the eigenvalues. You know the eigenvalue problem, simply lambda I minus a is that system matrix that we are talking about, and we find out the values of lambda. So it's a quadratic equation, we have two roots. Now those eigenvalues, they give us the behavior in phugoid mode. So somehow we are able to compute the natural frequency and damping ratio of that phugoid mode. So you see that natural frequency depends on the velocity at which the aircraft is operating, and damping ratio depends on the lift to drag ratio, right? So these calculations are hidden here, but in general the idea is this. I'll show you one photograph. So for phugoid mode, this is the idea. What happens is, if the aircraft is in the phugoid mode, your aircraft will have change of altitude. So it will exchange energy. So what is happening here? Aircraft is going down and the change in angle of attack is almost zero, but its altitude is changing, which means it's gaining velocity, right? The gravitational potential energy is getting converted into its kinetic energy, and then it goes up with almost no change in angle of attack. So what is happening here is altitude, the kinetic energy and potential energy are playing here. Okay, so this is the motion. So this kind of motion, when you observe on an aircraft, and the period of this motion is about 30 seconds or more, on that order for normal aircrafts. So what happens is these oscillations that you see in its altitude, they dampen over time, which means they reduce in magnitude over time. So that damping we were talking about, that damping depends on lift to drag ratio. If you have a large lift to drag ratio, you will have low damping, which means the oscillation will be sustained for a longer period. Similarly, I'll show you first what the equations for short period motion are. For the short period, we ignore u and theta. Instead, we take w and q. So we observe this 2 cross 2 matrix, and this w is written again in terms of angle of attack, because it's simply change in w divided by the horizontal velocity of the aircraft. It gives you angle of attack. So you have angle of attack and pitch rate dynamics. Okay, so this dynamics is short period. It means changes in angle of attack will die quickly. So this is, I'll show you again what is happening here in the second graph. So this is change in angle of attack and it dies quickly. So the time period of this kind of short period motion is on the several seconds, means less than 5. So for normal aviation aircraft, it's on the order of 5 seconds. The period for phugoid mode is on the order of 30 seconds. So your aircraft angle of attack is changing quickly, but it dampens out. So the oscillations are stopped uh, after a few seconds. So that is your short period mode. So ultimately, what I wanted to give you is, where do this question came from? When the center of gravity of the aircraft move rearward, then the effect on long period mode will be. So that was the long period mode. This was a long period mode. Your aircraft is oscillating. It is experiencing changes in its altitude. So that's what we call the phugoid mode. Now, I think
So,
ma-
sir,
uh,
actually, this was pertaining to the static and dynamic stability of the aircraft.
yeah,
Okay.
yeah.
So,
So
this was the mathematical analysis for
yeah,
it.
Yeah, I just wanted to give you like where these terms come from. So if I simply tell you, then probably you won't understand. So I gave you some background that you have to understand the dynamics of aircraft. Then you linearize it. Then you apply certain approximations, and then you understand. Okay, the aircraft behaves in two distinct manner. One in which there is a long period, and the second in which there is a small period. So for the long period, oscillations occur between the altitude and the velocity, and for the other one, oscillations occur between angle of attack, right? So but you can answer this question: less stable as compared to last center of gravity. My aim was to teach you what long period is. Okay. Similarly, you see the short period motion, exactly similar kind of equation. You see, uh, this is short period, and oscillations will happen in angle of attack. So this W can be written in terms of angle of attack also. If you don't write, doesn't matter because they've given things. So this is your system matrix. What is happening here? The numerical value of A and B will be, take damping ratio and undamped natural frequency are 0 and 5. So what you will do is, you will make sure that the eigenvalues of these matrices, they are such that they satisfy these two things. So what you do, you take the eigenvalues of this. So you find out eigenvalues in terms of A and B. You end up with this equation. You compare this with this general equation of the second order. Okay, are you guys aware of the second order equation, this that I have just highlighted? Anyone aware of this equation? What does it represent? Omega n and zeta? No. So zeta is basically damping ratio, omega n is natural frequency. So I'll explain what the terms mean. Okay, with a spring mass damper system just in a moment. But here, just bear with me. So you compare these two equations, and you find out. You simply enforce these two relations. So damping ratio is given to be 0, so zeta is 0, and for zeta to be 0, B has to be 1. And then you enforce the omega n natural frequency to be 5. When you enforce that relation, and you know already the value of B, A turns out to be minus 26. So now I'll explain what the second order equation really mean. So how do you write the how do you write the equation for spring mass damper system? Something like this: mx double dot, you have then cx dot, you have then some kx equals 0, right? That's how you write equation for spring mass damper system. Is everyone aware of that? All right, so this is your mass m, you have spring constant k, you have some damper here, right? You place a damper. So I don't know how they draw it, but that's a damper. All right, so you take a Laplace transform of this equation. What you end up with is
Frequency domain
yeah.
analysis.
So what you end up with? So x of s. I forgot to write x of s, and I forgot to write x of s. So you take x of s as common, but you finally end up with this cs plus k. And if you simply take s square plus c by m plus k by m, and this is s here, then your c by m is basically compared to zeta omega n, and your k by m is compared to omega n square. From there you find out that natural frequency for this spring mass damper is this, right? So this is second order system that we're looking at, and we are comparing so this equation is generally written in this form. So it exhibits certain properties, lambda, and I can't explain all the properties in this small tutorial. So this is general second order behavior, and what happens is when you solve a second order system, it'll exhibit different behavior and depending upon the values of omega n and zeta. Okay, so I'll suggest you read a second order system, simply second order differential equation, linear second order differential equation, and what are the different solutions for that. And the solution will have different behaviors depending upon what zeta and omega n are. And if you want a reference, I can give you this book. It's Robert C. Nelson, and this book's chapter 4 will give you a complete idea of what a second order system looks like and how it behaves. So it is the second order system here. Pure pitching motion is compared to this, right? Now, depending upon zeta and omega n, or any other second order system that you have, so we simply solve this system and we try to look at the behavior. For example, it's overdamped when your zeta is greater than 1, and underdamped when your zeta is between 0 and 1, and critically damped when your zeta is exactly 1. Okay, so these three different behaviors for the same differential equation. So that is the idea. Okay, so you have to do a lot of background study to fully understand that, but I can give you just idea. Chapter 4, Robert C. Nelson, you can study this part, and almost every book on vibration will also teach you that. So yeah, let's go ahead. So this is question 3 for us. The necessary condition of stable aircraft is, I think everyone is aware, Cm alpha has to be less than 0. Is anyone unaware here? Akhileshwar, are you aware that?
We are aware that.
Yeah, everyone is
Yes,
aware
I'm
because
aware.
it's the end of the course and everyone should be aware of this. Which condition holds to trim the stable aircraft at positive angle of attack? We've discussed this thing in 2-3 lectures actually. Cm alpha has to be less than 0 and Cm naught has to be greater than 0, and then you have a positive uh, trim at positive angle of attack. If anyone has any doubt, they can ask me. I can explain in detail. No? All right. Everyone understands probably. Which condition holds to trim the stable aircraft at zero angle of attack? So simply shift this line, this red line, to origin. It must pass through the origin. Wherever it intersects the alpha axis, that is your trim angle. Because what trim really means is Cm has to be 0. So Cm is 0 at this angle. Similarly, in this graph, Cm is only 0 at alpha is equal to 0. So this is the answer. Cm alpha is less than 0, Cm naught is 0. So that's the answer. Now you have 4 more questions. Some data is given to us. Some formula are also given to us. The location of neutral point in meters of the above fixed wing UAV from the leading edge of the wing will be. So how many of you can derive this formula or know the meaning of this formula X and P? Can anyone derive or explain what really this formula is about?
Sir, I'm unaware of the term neta T and epsilon. Rest I know.
Rest you know. So neta T is simply what they call is, it's a ratio of the dynamic pressure experienced at the tail uh, with respect to wing. So it's a ratio of two dynamic pressures. Now you recall, because see, when we were studying about stability, we were looking like this. So this is your tail, this is your wing. There will be an air coming like this, certain angle of attack. So the air going here will be different because of the downwash here. Also, the dynamic pressure here will be different. So V infinity is different. That V infinity won't be reaching there. So it might accelerate or it might deaccelerate. Both can happen. So this neta T that we're talking about, it ranges from point 8 to 1.2. Air can accelerate also, right? At certain parts, the way you configure the location of this tail. So based on that, so for typical aircrafts, neta t is usually taken less than 1, and it's on the order of zero point 0.9. So it's a ratio of dynamic pressures. I'm sure you know what dynamic pressure is. It's this quantity, dynamic pressure. So q infinity at the tail, q infinity at the wing, and that is your neta t. The other quantity that you are asking about is epsilon. That epsilon is basically the downwash angle. The downwash angle is what? If your vector of velocity is oriented like this, because of the downwash, it's oriented in this fashion. So this is your epsilon. By what angle the velocity vector has been pushed down for the tail? So downwash. So we've discussed these things in detail, and you can also refer that same book, chapter 2, Nelson. They have a discussion on it. So this whole thing comes into picture when we compute the angle of attack at the tail, because the angle of attack experienced by the wing is different from the angle of attack experienced at the tail. So when we compute the angle of attack at tail, this downwash angle come into picture. But can anyone intuitively explain me intuitively where does this come from? Okay, I'll tell you.
Can you just repeat the question, please?
Can anyone intuitively explain where does the expression for x and p come from? So that expression, we are supposed to compute neutral point of the aircraft, and by this point, because this is the last lecture, I assume everybody is aware of what neutral point is and all other quantities. So I won't go into the definition, but rather explain where does this expression come from.
In the numerator, the first term actually is the amount of pitching moment that is generated by the wing. That is CL alpha wing into the X AC wing.
Okay.
And the second is how much is the pitching moment that is being generated by the tail, which is inherently the one which will counter the pitching moment.
Okay.
Uh, that those two terms are, and the ST upon S is actually the tail volume ratio, which is determines how effective the tail is in countering the moment that is generated by the wing.
Okay. So you're somewhat correct, but not exactly what I wanted to hear. So I'll try to explain what I wanted to hear. What I wanted to hear is we have two aerodynamic elements here. One is your wing, one is your tail, right? They are generating lift, and their lift is characterized by the CL at the wing and CL of the tail. And the net CL of the aircraft will be CL of the wing and CL of the tail, and rather CL alpha. I think we use the lift curve slope here. Yes, that's CL alpha. Okay, so CL alpha of the wing will be simply addition of these two alphas, CL alphas, right? So this is your net CL alpha of the aircraft. Now, this CL alpha explains the lift generation capacity of that individual aerodynamic element. Okay, right? So now, how basically neutral point is the aerodynamic center of the whole aircraft. That is the definition, one of the definitions, right? So where do we place the lift on an aerodynamic element? At what point we say that we will place the lift?
At the aerodynamics.
Good, at the aerodynamic center. So we are saying this is your leading edge. All distances must be measured from here. This is x AC of the wing, and there should be some AC for the tail with respect to this point. So The lift is being generated at these 2 points, xac of the wing and xac of the tail. Where should the aerodynamic center be? Whoever generates more lift will attract it more, right? True? That's what is happening here. So, how do you compute center of mass? You have mass of one body, location of the mass, second mass, location of the second mass divided with total mass. Similarly, who has more contribution in lift generation? So, what we'll do is we have CL alpha of the wing where it is being generated, CL alpha of the tail where it is being generated. CL alpha of tail is slightly complicated because it involves certain quantities, something like this. So this whole thing is basically CL alpha of tail multiplied XAC of the tail divided by net CL, which is net lift curve slope. CL alpha W plus CL alpha tail, the whole expression right here. If you go back and check the expression, this is exactly that is CL alpha of the wing, XAC of the wing. This whole quantity is CL alpha of tail, XAC of the tail, and this is the net lift curve slope. So this is easy way to remember it, okay? XNP location. And the other means to compute is, that is standard way. Standard way is what? You compute an expression for CM alpha. You have contribution in CM from wing, contribution in CM from tail. You make CM alpha 0. And then wherever your CG is, make this, wherever your aerodynamic center is AC, make it the neutral point X and P. So replace your XAC with X and P, and then you have neutral point. So that is the standard way. Okay, so since it's a numerical question, the numbers are given. You can just look at in the table and compute everything here. All we need to understand is what this expression really means for us. Now the total lift curve slope for the UAV. So total lift curve is here at the bottom. This same quantity you compute, everything is given. We're done. Similarly, CM alpha and CL alpha, we compute the ratio. The numbers are given to us. Okay. So this is SM. This expression is very well known to you. There are multiple questions on it. SM is known to us. Then we know the definition of SM, and from there on we can compute the location of XCG. When we know what we know, X and P, we know, we just computed it. So XCG we need to know. C bar is also given, so you can compute it. Horizontal tail volume ratio. I think everything is given. You can compute it from direct expression. Okay. So all you have to do is remember the definition of what horizontal tail volume ratio is and how do you define SM. But if you have conceptual doubts in their definition and understanding that, you can ask me. And other than that, this is simple standard question. You have some numbers, put in the formula, you have the answer. Right? So I think 1 hour is already gone. If you have any questions, you can ask me. If not, you can leave the meeting.
So here, how did they calculate the tail area ratio?
Okay. So what was the definition of VH? I think this was the definition: ST some L divided by SW divided by C bar. This was the right expression for VH.
Yes.
What was this L? This was X. This was the no, not this one. L was the distance from CG. This is your CG, XCG, and from there you had how far your tail is. So that was the length L. So we know all lengths from here. We know where is XCG. We know where is x. What do I call that? Uh, Aerodynamic center, x AC of t. What you can do is you can take x ACT minus x CG and you end up with L. That L sits here. Everything else is known to you. Yeah, that's exactly what is done. You understood now.
No, I was talking about the area. S upon S is not directly it's how it is confusion.
It's not given or what? 1/4. Let's see. I don't actually, I haven't solved this question. I thought there are numbers. This ratio is also given here, ST by S 1/4. So how did they get it? What information do we have here?
It's given in the first line, tail area is 1/4 of ring area.
Exactly. So the ratio is given. It's here. It's not in the numbers. It's here written. So the ratio is known to us. Yeah. If you have any other question, you can ask or you can leave. Because I think I'm feeling tired. I won't be able to teach anything else apart from this assignment today. I had a lot of work today. But if you have any other questions, you can reach out to me. I'll give you my email. Okay, just in case, because you guys have exam, and if you have any conceptual doubts, you can reach out to my email. I'll give you that with your questions. So I'm open for help until your exam is over. So this is my email. You can email me your questions whenever you are preparing for the exam, and you feel like you don't know the source, how to understand it, or any questions that you have. I'm sitting here for the next 1 hour also. So if you're solving questions and if you have doubts, you can ask me. Okay, I'm here in the meeting. If you have doubts, you can ask me. So take this 1 hour as an opportunity to prepare for the exam. Go ahead and try to solve questions. Whatever questions you have, throw at me. Okay. Vijay has asked, there is doubt in assignment number 11. Okay. We'll come to you, Vishwa. First, let's see what Satish has got. CL versus alpha, CM versus CL, CM versus alpha. Okay. CL versus alpha. For a cambered airfoil, it looks like this, and for a symmetric airfoil, it looks like this. Now, what exactly is your question? I mean, the curve looks like this. So you have an airfoil, or rather a wing. So for the wing, the slope will be little modified based on how much aspect ratio you have and what is the shape of the wing plane form. So I'll explain that later. But this is the general curve, a simple linear curve, and this is the angle alpha where CL is 0. So alpha CL is equal to 0 angle. This is called, and CL general expression can be written as CL naught plus CL alpha times alpha. So usually this is valid in this range. So it's not valid near stall. So this is some high angle of attack. So it's not, this expression is not valid here in this regime, but it's valid for small angles. And CL naught is this length. Now, what specifically you want to understand about this? And the other thing you asked was CM versus alpha. So CM versus alpha. This looks like this for a stable aircraft. This looks like this for an unstable aircraft, and this looks like this for a neutrally stable aircraft. Idea is CM alpha has to be negative. Okay, so the slope of this line has to be negative between CM and alpha. And if you want to trim it at positive angle of attack, this is your CM naught, and this is your alpha trim. This is the trim angle. Okay, trim angle is where CM is equal to 0. So CM is 0 for this angle. So CM naught has to be greater than 0 if you want to trim at a positive angle of attack. So these two conditions must be satisfied. Now the third question that you asked was CM versus CL. CM versus CL is nothing but CM versus alpha actually, partially. Because if you multiply this alpha with CL alpha, right, and add CL naught, then it becomes CL. So it's virtually the curve between alpha and CM. So it also looks like this. But obviously the slope will be different, right? But the nature of the curve will be similar. So this will be your CL trim wherever your CM is equal to 0 for which CL, that will be CL trim, and it will be alpha trim. So someone asks they have doubt in question assignment 11. What is the doubt in assignment 11?
Sir, in assignment number 11, it is regarding the calculation of the fuel fraction for a given range.
Okay.
Now, in this, what will be considered is that the fuel that is required, that is W1 upon W0, is only be considered. The fuel for takeoff, landing, all those fuel fractions have been neglected.
Yeah, actually we discussed that in that session also.
Okay.
Hmm.
Because if you calculate it with that, the answer comes out to be completely different. I'm sorry I didn't attend the problem solving session.
Hmm. But the thing is, answer will be different. But how will you compute for landing and takeoff? Like how? I mean,
Actually, in the Tramer's book, it is given for taxi and takeoff fuel fraction is 0.97.
yeah, but
For approach and landing 0.995.
that is perfect. That is perfect when you solve a realistic problem. It was simple assignment problem, and your scope is what data you have been given, right? So you compute based on that only.
Okay, sir. But so if even if it is the exam, you should just take it as R max is the.
Your voice actually broke in between.
No, sir, that is fine. But even if it is there in the exam, we
Mhm.
should not take the fractions for takeoff and landing and everything. Right?
Yeah, because see, the idea is you can take a different fraction. You can claim, okay, I did for this aircraft. Someone else can claim, okay, I did for that aircraft. And then there is a conflict. So examinations have scope only with respect to the questions. So what information you have available in the question, you answer based on that. But in real life, you're 100% correct. If you design an actual aircraft, you always have to consider landing and takeoff.
Okay, so that was the only thing because my answers went wrong because I considered the
Yeah, yeah,
Raymer figure.
yeah, yeah. So try to stick to the questions only. Okay.
Sure.
Hmm. हेलो. हाँ बोलो. शिफ्ट. तो उसकी कंफर्मेशन आएगी क्योंकि तुमने ईमेल भेज दिया ना. कोई कंफर्मेशन तो आनी चाहिए, हाँ या ना में. ये शिफ्ट. तैयारी करते रहो, वेट करो. देखते हैं, आपको जॉब देगा उसी के बेसिस पे कोई बात कही जा सकती है. हाँ, देखो क्या होता है. तुम तैयारी करते रहो, ज़्यादा मत सोचो. बस वही है. वही सब कुछ है तुम्हारे लिए. वही भगवान है. सब कुछ. हाँ.
Sir, I have one question.
Yeah.
Sir, regarding the assignment 11, set 12,
Mhm.
the sixth question, can you please elaborately explain, sir?
Yeah. I explained it actually a little while ago, but I'll do it again for you.
Okay, thank you,
Yeah.
sir. Thank you so much.
So the idea is you have two aerodynamic elements. One of them is wing, and one of them is tail. Okay.
Yes,
So
sir.
we force that the lift is being generated at aerodynamic center. In reality, it is generated at center of pressure, but we shift it here
Okay,
deliberately
sir.
to make the calculations easier for us. And that shifting comes with the moment. So I mean the torque, right? And this is XAC of the tail, and this is lift of the tail, lift of the wing. So aerodynamic center should lie somewhere in between, right?
Yes,
So
sir.
depending upon which one is generating how much lift, or which one has larger lift slope. So the reference point is the leading edge, and this is the location of XAC of the wing, and that is the location of XAC of the tail. Now, your wing has a lift slope CL alpha of W, and your tail has a slope of CL alpha tail, and then there is a factor. And what is that factor? Some efficiency factor, some ratio of the area, and 1 minus d epsilon or d alpha. So this whole number is basically CL alpha of the tail, the overall lift curve slope for the tail. And where does it come from? You can refer to some book. I'll specifically tell you Robert C. Nelson. But here you just take my word. This is CL alpha for the tail, and this is CL alpha for the wing. Now, how do you compute center of mass? The algorithm is mass of you have multiple point masses. So what you do, m1 x1 m2 x2, and then you divide it with total mass, right?
Yes, sir.
Similarly, you have lifting elements. So Cl alpha of W, where is the location? XAC of W. Then you have another element which is Cl alpha T, 1 minus d epsilon over d alpha, and other numbers, neta, and the ratio of the areas. Multiply this whole number getting multiplied with XAC of the tail, right? That's the location. Then simply the sum of these two things, Cl alpha W plus neta T Cl alpha T, 1 minus d epsilon over d alpha. So it's basically distribution of lift between these two elements, and it should give us the x and p. So that's the idea behind this formula,
Okay, sir.
this expression. Now you understood, right?
Yes, sir. Thanks.
Yeah.
Sir, I have one doubt.
Yeah, go ahead.
Yes, sir. Sir, in the formula of CM, CM not CM not of the wing is equal to CM not aircraft wing plus CL of wings XCG bar minus X bar into aircraft wing. In the formula, we can directly calculate by substituting this value on sixth assignment, 12th assignment on sixth question. Shall we get the answer?
Uh, wait. Can you show me the formula? You can share your screen if you want,
Okay, sir.
or you can speak again. I'll try to write it. I could not follow
Okay,
it.
sir. Yeah, okay, sir. Actually, one more thing, sir. I have one doubt on. Sir, what means CM? CM is the coefficient of static margin, am I right?
No, CM is pitching moment coefficient.
Pitching moment coefficient. And CM not, sir.
CM naught is just a number actually. I don't know how to explain that. It's just an intercept in that curve. I'll tell you what is that.
Okay, sir. CM alpha is the
Yeah,
pitching
yeah,
angle.
yeah.
Angle of
CM.
attack, am I right, sir?
So CM naught is
Uh,
just this intercept.
okay, sir. And CM delta E is the elevator angle of attack, am I right?
Yes, absolutely.
Okay, sir. Right now, the any flight is going on flying,
Mm-hmm.
the wing we going to setting on positive angle, which means it generate lift.
Yeah.
1 degree will be there,
Yeah.
it generate lift. While we adjusting the stick will be there, it's adjusting the elevator.
Right.
Okay.
Right.
The elevator only we doing only stability using. That's not generating lift. Am I right, sir?
Right. Absolutely.
Okay. Elevator only using for stability.
Right.
There is no lift. Okay.
However, lift increases, right?
Okay, sir.
But the magnitude is not really large, but it helps us trimming at different angle of attacks. Let's say you want to change alpha, so you can change delta E and still keep the CM to be zero, right? You can raise delta E and lower alpha and then keep,
Okay.
yeah. So that's how we do.
Oh, Kemper Raphael, it's possible.
Yeah.
Okay, sir. Thanks.
Sir, hello sir. May I audible? Vikram sir, may I audible? Vikram sir, hello. Hello sir.
Yeah, go ahead.
Uh, Sir, in CL delta E, that formula is tau neta T ST by S. CL alpha T.
Mhm.
ST means the area of the tail, right sir?
Yes, perfect.
So, sir, S means
What means?
ST by S. ST means area of the tail,
Ah,
right sir?
and by
S means
S, area of the
yes.
wing. Yeah. And you are given ST over S in that particular question.
Yes sir.
Hmm.
Sir,
Hmm.
I don't understand.
Okay. You're talking about this, na? You're talking about this, right? ST over
Yes,
S.
sir. Yes, sir.
So S is the area of the wing, ST is the area of the tail, and you are given the tail area is 1/4 of the wing area. So ST
Okay.
over S is 1/4.
Okay. Always say yes means na area of the wing only. Okay, sir.
Sometimes they will write it as W, but I mean you can write whatever you want. So usually write as W also. So
Okay, okay, okay.
yeah.
Thanks. Sir, one more request, sir.
Yeah.
Sir, sir, this question answer session is very useful for us. Sir, can you please arrange one more session on Friday or Saturday, sir? To us, it's very useful for us.
Okay. I mean, officially it ends today, but if you want, I have written my email, so you can write me on my email. Then I'll send you the link, or anyone who wants to join.
Okay, sir. Thank you so much, sir.
Yeah.
Sir, just a question, sir. Will all these formulas be provided as a part of the exam? Because remembering them is very difficult.
I believe no. Maybe if the question is big like this, they may give you something, right? But expect nothing. Prepare for everything.
Okay, sir.
Yeah.
मैं सोच रहा था कितने सीनियर नेता को बीजेपी ने टिकट क्यों नहीं दिया। कर्नाटक में बीजेपी को उन्होंने खड़ा किया, क्या इनको बीजेपी से निकाल दिया। उन्होंने कहा मेरे बारे में कोई टेप नहीं, कोई भ्रष्टाचार नहीं, उन्होंने इनको टिकट नहीं, मतलब इन्होंने इन्होंने 40% नहीं, तो ये 40 नंबर अच्छा लगता है इस बार 40 देना है। डॉक्टर जी बोल रहे थे ಇನ್ನೊಂದು मैं सोच रहा था आप यहाँ पर आदरणीय नीतीश कुमार जी और यादव जी हमारी पार्टी, मैं सबसे पहले आदरणीय नीतीश कुमार जी का यशस्वी का स्वागत करता हूं। लखनऊ में और जिस तरह का लोकतंत्र पे संकट है, लोकतंत्र को बचाने के लिए, संविधान को बचाने के लिए भारतीय जनता पार्टी की लगातार सतत आर्थिक आंतरिक संकट में आई चरम सीमा पर, रोजगारी चरम सीमा पर, और इस भारतीय जनता पार्टी को हटाने में हम आप लोगों के साथ हैं। भारतीय जनता पार्टी के देश बचे,
उस अभियान में हम लोग आपने और बाकी सबसे ज्यादा ये आगे बढ़ाने और यहाँ शासन करते हैं आपने बनाना है साथ साथ कृषि पार्टियों के साथ बातचीत चल रही है पार्टियों करें और मिलकर के सब काम करें ताकि देश आगे बढ़े देश अच्छे रहे देश के को बदलने का साथ और okay then guys you can leave the meeting now.
Thank you so much
Yeah.
for your time.
Yeah, thank you for
Thank you very much, sir. Thank you.
Yeah.